All right, do we have any questions before we start today? So review class is on Monday as well as homework number 3 being due then. Make sure you hand in homework number 3 or submit it on Blackboard before the class begins. I haven't gotten any review questions yet, but send me emails if you want to review any specific topics in that review class. Otherwise, if you guys don't want to review anything, we don't have to have that class. It's for you, not for me. So there are no questions. Let's continue with our underdamped second order systems. I have one more class on that at least. All right, so let's talk about our poles for an underdamped second order system. So our poles, which we solved for last time, was negative zeta times omega n plus or minus our imaginary number j, omega n, square root of 1 minus zeta squared, right? We also could have said zeta times omega n, that is sigma d, the real part, right? And then the imaginary part is omega d here. All right, and so what we're going to do is just graph this out on our real and imaginary axes for our poles and zeros. So sigma j omega, right? We have two poles here, right? They are going to be located at negative sigma d. Let's say that's like right around here. And then let's say this is plus j omega d and minus j omega d here. So our two poles would be located at these spots, one right here, one right here. They're both complex numbers, so they're in the second and third quadrant here if it's a stable system, right? We can also write this out, have a little triangle here, right? We could do the same down here as well, where we would have, this is going to be an angle theta here. And this hypotenuse of this right triangle is going to be omega n. So we can get a right triangle, right, that is going to relate, that's going to relate the real part, the imaginary part, and our natural frequency here. And this angle theta, which is going to relate to actually zeta, as we're going to see in a second here. Okay, so let's start with, these are our baseline poles. And what we're going to do now is we're going to study what happens when we change the poles. All right. And we're going to, again, say this is for same transfer function as last time, where we don't have any zeros in our system. All right. Some important parameters here that I want to remind you guys of. One was our settling time, which was 4 over zeta omega n, or 4 over sigma d, right? A peak time, TP, which was pi over omega d. And then our percent overshoot, which was 100. And then exponential, that relates to that damping ratio. So we're going to look at 3 different cases for step responses. I'm just going to take a plot straight from NYSES textbook again here, the one from the course, and just throw it over here. All right, so let's focus in on this first case here. So the first case, so this is from the 6th edition, nice 6th edition. This is figure 4.19 here. And this first case, I just want you guys to focus on this box right here. We're going to change the imaginary part only for our poles. We're going to increase the imaginary part for it. So looking at these parameters here, what happens as omega d increases in magnitude, what happens to our response, right? We can see our poles are increasing only along the imaginary part. The real part is staying exactly the same. Look at our results here. If we were to have a step response where C is our output in this case, what happens? Or maybe look at our parameters. What happens when we increase that imaginary part?
Frequency of the oscillation.
So frequency of oscillation, what happens to it? Right? Why does it increase? Why does that make sense? What is the frequency of oscillation for an underdamped second order system? We went through it last time. Which frequency? We got like two of them, right? Natural frequency and damped natural frequency. Which one is appropriate for a second order system for its actual observable frequency here? It's the damped natural frequency, right? That was the one that showed up in our cosine solution, right? So this makes sense. If omega d increases, right, our frequency of that cosine wave is going to increase, right? What else do we see here? Is that the only thing that changes in our response? Overshoot increases, right? We can see here, case number 1 just had a little bit of overshoot. Case number 3 had a lot more overshoot. What else? Those are the only two things that change here. Peak time reduced. So peak time decreases. Anything else? How long does it take to get to steady state between these options? What parameter up there describes steady state or relates to it? Settling time, right? So what happens to settling time in this case? Does it change? We have a formula for settling time here, right? What's the settling time relate to? What part of our pole? Only the real part, right? And so what have we changed in this case? The imaginary part, right? The settling time is constant, right? All three of these take the same amount of time to get within 2% about of its steady state value here. Settling time, right? It's relating to whatever is in that exponential we went through last time. Settling time is more or less unchanged. Okay? All right, what about our second case here? So now let's make our real part more and more negative, but we're going to keep the imaginary part the same. So we're going to go this way. Right? Our poles are getting more and more negative for the real part. So as sigma d increases in magnitude, what happens? What do we got? What's going on here? Settling time decreases. Very good. Right? Our real part is getting more and more negative. That means the thing in the exponential is going to be more and more negative, right? Multiplied by t, which means that exponential is going to decay faster. We're going to reach our settling, or reach our steady state value much faster. What else? Our overshoot decreases, right? What else? There's one that's already in the plot, gives you the answer, right? The frequency of oscillation is the same, right? Omega d hasn't changed at all, right? These two things are oscillating at the same frequency. All right, last case. So now we're going to increase our poles, the magnitudes of them, specifically, we're more or less increasing omega n along the same angled line here, right? So what happens in these cases? Right, so this is more or less only omega n changing. Same theta, omega n increasing. What happens? The big thing is that these all have the same overshoot, right? Those angled lines for our poles, right? These lines coming out from our origin, right? Those are associated with our overshoot. What other parameter is associated with overshoot? Did we say before? It is, you're right. Think in terms of our general second order circuit or second order system parameters. What does that overshoot equation depend on? Max overshoot, what does it relate to? What parameter? Zeta, right? Our damping ratio. Overshoot, damping ratio, those are connected. Make sure you understand that, right? So these straight lines here, right, with the same angle, if they have the same overshoot, that means that they have the same damping ratio. Okay, so let's go through an example here. So I'm going to give you guys a figure. I'm going to try and draw this out properly. We probably won't do a great job. I'm going to give you the poles of a system. So this is our real and imaginary parts here. And our poles are going to be located at, this is 2. And 4 here. The one pole is here, one pole is here. We can, of course, draw it out a little angle here. All right, so we have this system. I want to do two things. For part A, I want you to determine our damping ratio and our natural frequency. All right, then for part B, I want you to change the pole location to maintain the same percent overshoot, but decrease settling time. And so specifically, I want new zeta and omega n values. Okay, so we have several options for approaching this. What's your guys' recommendation? Let's start with A. How can we figure out, if I just give you these poles here, what zeta and omega n are? There's several different ways that we can approach this. Okay, all right, guide me through it. I think that's a great idea. Okay, well, let's first draw out the triangle that we're talking about here and label it, right? If you want to use trigonometry. Okay, that's theta, right? What should I label the other parts here? Say again? Omega n is our hypotenuse here, right? Good. What are our other pieces? This is omega d, right? And the last piece? Sigma d, right? Okay. So we got a bunch of variables here. Yeah, what are they? 4 and 2. Okay, good. All right, I'm looking for zeta and omega n here. So sigma d squared plus omega d squared is equal to omega n squared, right? That's what you're saying. So what do we end up with for omega n? If we were to solve this equation here. Square root of 20, right? 4 squared plus 2 squared, that's 20. Square root of that. So we end up with the square root of 20. We got one parameter already. Okay. Now, how do we get zeta? What's omega d equal to? Zeta times what? Omega n. Okay. So what do we end up with for zeta? All right, we just solved for omega n. 4 over the square root of 20, right? That's one way to go about doing it. Another way that we could do it is, I think somebody suggested solving for the angle earlier, right? That's another option that we could have done, right? Cosine of theta would have been sigma d over omega n, or zeta omega n over omega n, right? Or cosine of theta is just zeta there, right? If we can figure out what that theta is, right? Probably using omega d and sigma d with the arctangent, right? We could also solve for zeta there, right? We can see zeta is equal to the cosine of theta here. That's another relationship here. That's showing that that angle that I was talking about, right? The angle is associated with constant zeta values here. Okay? Any questions on the first part here? Not, let's go through B now. So now I want the same overshoot, but I want to decrease settling time. Give me a new zeta, give me a new omega n. Okay. Increase along that angle, right? Increase what values? Sigma d and omega d. Okay. Remember, I'm looking for a new zeta and a new omega n. You guys aren't saying anything wrong. Maybe just like inefficient, I guess, or not complete. Increase sigma d and WD, is that what you said? Okay. Uh-huh. Uh-huh. Yeah. Still saying the right things, but we're not quite there, right? Or maybe like a little bit incomplete here. I'm looking for values, guys. Why would the damping ratio be the same? Right? We said that that angle is constant, right? That means that zeta is constant. That means that our overshoot is constant, right? And I want the same overshoot here. Zeta needs to be the same. What happens to omega n here? Let's not talk about omega d and sigma d, right? That's like a couple extra parameters here. What do I want to do with omega n? I just want to increase this. For this simple problem here, yeah, you could double it as long as it is greater than the square root of 20 here. Right? We're good. Right? That's it. That's all I was looking for in this problem. Any questions on that? Right? We're getting closer to actually starting to design things here. Right? This is a very basic example. Okay. No questions? Let's move on to like a full-blown example here. So this is going to be primarily what we're covering today. I guess we can make it an in-class example. We'll break it up into pieces. But I want you guys to do the following for the system I'm about to draw out. I'm going to want you guys to get the transfer function for this system. Then I'm going to want you to determine zeta and omega n. I want you to tell me if the system is underdamped, overdamped, etc. And then I want you to change one of the original parameters to get an underdamped system underdamped response for a step input with 10% max overshoot. All right, this would be a pretty solid homework or exam problem. Obviously not for this first exam coming up, but maybe for a future exam. So our system, we have a source voltage, we have an inductor, and then we have an RC pair, capacitor and a resistor connected in parallel. Pretty basic circuit. L, C, and R, right? Our output is the voltage of the resistor. We have zeros for our initial conditions. And let's say C is equal to 2 farads, R is equal to 0.1 ohms, and L is equal to 200 henries, as I believe the unit. All right. So let's start with A here. Maybe we'll do this one together just to get the ball rolling. All right, 4A. We want to get our transfer function for this system. Input to output, right? You guys have done probably homework number 2, was it? This is homework number 2 was a harder problem than this, right? So this one should be easy, right? Okay, so guide me through it. Let's work on it together, since you guys should be experts on this by now. How do we get a transfer function for this system? Okay, good. So let's start by doing the impedances here. So that's the inductor. That's our capacitor. That's our resistor. What happens to the voltage source with our impedances? What? It remains the same, right? Except we would do a Laplace transform on it. So it'd be V of S. Okay, good starting point. LS, 1 over C times S. And then resistors are easy. It's whatever the resistance is, right? Okay. Good start. Okay. Like the total equivalent resistance? I think that's a good idea. I would suggest to do something briefly before that, right? Which is, what is our input and our output, right? What are we trying to go for here? I'm not asking for total impedance for this problem, right? May be useful, but let's remember what our objective is here. What are we trying to get? Transfer function, thank you for being the one that doesn't whisper it. Transfer function from what to what, right? Right, so this is our input, right? That's our source voltage, right? And then where do I want to label my output here? What about the resistor? Right, that's the key part here. I think some people had some questions about that with homework number 2, right? I'm specifically asking for the voltage of the resistor in this case, right? I could have said the current as well. Okay. Anything else you guys want to label here that may be important? Maybe, maybe not. The voltages, sure. So plus to minus, plus to minus, plus to minus, all right? Anything else? I'd probably throw a current out there, at least for the total circuit. Maybe not necessary. We'll have to find out. We could also have currents for the individual resistors and capacitors here. Not sure if that's going to be necessary or not. All right, suggestions. Voltage law. Okay. Current law, voltage law. What do you guys want to do? Okay, so you want to label, let's call this I2 of S and I3 of S. You could do that. All right. I'm not sure that's going to be the most efficient way here, but you can absolutely do it and you will get the right answer. But there's something that would be a bit of a shortcut. Right. So if you went through and used the current law here and probably combined it with the voltage law at some point, you would end up with the equivalent of these are two elements that are in parallel here. Let's just combine them, right? So let's try that out. We have L times S, and then I am going to combine both of these elements. What is the combined impedance for both of those elements there? One over CS plus R. CS plus one over R. You guys got to review how to combine impedances or resistances in parallel, right? And so we can combine it together, right? Make it something that looks a little bit cleaner, right? And I think that should be R over RCS plus one if we were to combine them together. Yeah, something similar to that. Okay. And why did I do this? Why did I recommend this is the way to go? What? Where's our output? What happened to our output? Where is it? It's in that fraction? Right? These were two elements in parallel, right? The voltage of two elements in parallel are the same thing, right? This is why I want to combine them together. Because even when we combine them together, we still have our output directly represented here, right? Okay. What do we do from here? So this is plus minus, plus minus. This is I of S, right? And suddenly we don't need the current law anymore. Okay, so what is it going to be? What's the form? Y of S is equal to U of S minus LS. Where are you getting that from? Voltage law? Okay. Sure. All right. So maybe just for everybody else, U of S minus LS times I of S, right? That is equivalent voltage minus R over RCS plus one times I of S. Or you could just say that's Y of S, right? So using the voltage law here. Okay. And then you were saying to solve for Y of S. That's clever. I didn't personally do it that way, but that's actually a clever way to go about doing it. Is this it? Are we done? Do we have a transfer function? We need to get rid of I of S, right? How do we do that? Okay. Well, the transfer function is equal to the total impedance. I like the first half of what you said, so I'm going to pretend that you stopped there, right? How about let's get our total impedance and see what's valuable from that. All right, so what's our total impedance? All right, we're just going to combine these elements. What are they? Parallel, series? right? So it's going to be LS plus R over RCS plus 1, I think. Where's Y? Right? It doesn't actually exist in the circuit. We would have to split it up again, right? Okay. Can this help us at all? Remember, what are we trying to do? We had this Y is equal to U minus LS times I. We want to get rid of that I. So right? And then how about we solve this for I of S? I of S is going to be 1 over Z total times U of S, where this is Z total here. We haven't simplified it just yet. Okay. Now what? Right, let's plug in I in here. Y is equal to U minus LS times 1 over Z total times U of S. Right? Or we can combine those terms with U's. Right? And then go through and simplify all of this. And if you were to do that, our transfer function should end up being 1 over LC divided by S squared plus 1 over RCS plus 1 over LC. And if we plug in the parameters that we had for this, we would end up with 0.0025 S squared plus 5 times S plus 0.0025. We're probably going to need both of these equations, both the generic one and the one with the parameters in it, or the values rather. Okay, I'm not going to go through breaking down step by step how to do this and reduce it down to this form here, but it should end up something like this here. So we end up with a second order system, right? That makes sense too, right? Because we had 2 independent energy storage elements in this circuit. We had a capacitor and we had an inductor. So we should expect to have an S squared or less in the denominator of our transfer function. All right, so that is A. So now for B, determine zeta and omega n. So you guys have done this before. Take a minute or two. Tell me what is zeta, or I guess omega n is probably easier to calculate first. And then what is zeta? Omega n is 0.05, good. Right, so we had S squared plus 5 times S plus 0.0025 is equal to 0 was our characteristic equation. S squared plus 2 zeta omega n S plus omega n squared. Thankfully, we had a 1 already in front for both of our S squareds here. Omega n squared is equal to 0.0025, or omega n is equal to 0.05. Good. We got that one. And then what is zeta? What was it? What? It's not point anything. It's 50. Are you trying to do math in your head? Don't do math in your head. I'm noticing a pattern with that. Okay, it's 50. It came out to a nice and clean number in this example here. All right, C was telling me what type of system this was. What type of system is this? For our second order categorizations. All right, we had like 4 or 5 options. And I think I heard overdamped somewhere in there. I think I heard way overdamped, right? Because zeta is greater than 1, exactly, this is an overdamped system. Okay. And now for part D, now I want to say change one of our original parameters. I don't want an overdamped system anymore. So we have this circuit and I say replace the capacitor, the inductor, or the resistor with a new one, with a new value to get an underdamped system with 10% max overshoot for a step response here. All right, so we want n% is equal to 10. Right. How can we go about doing that? What are your guys' ideas? Yeah. Okay, good. So we had a formula already. Zeta was equal to, I think I told you guys this one is important, 100 over max percent overshoot divided by the square root of pi squared plus that same natural log squared. Right? So let's calculate, if this is our desired percent overshoot, right? Let's find out what our zeta should be in this case. I don't know, do you guys have calculators with you? So crunch it out, let me know what you end up getting here. This is why probably for exam 2, you guys will need calculators, or I'll need to give you a table with these values already set up. 0.91, I don't think that's right. I'll write it down. I had something different, but my notes can be wrong with these types of numbers. I change the problems a lot. .59. That's what I got as well. So you may want to double check in case you're using like log base 10 or not the natural log here. Or maybe sometimes you forget to do square root or the pi squared part. I got 0.59. So that is a desired damping ratio we want to have for this system here. Do you have a question? No. Okay, so this is the damping ratio we want to get. So how do we change our circuit to get that damping ratio? What do you guys think? We're now redesigning a circuit. Can you say that a little louder? Plug in 0.59 in place of 50, okay. But which equation? This one? That had all the parameters already in it, right? You got the right idea, work backwards in some sense, but be specific with me here. We do want to use that zeta as 0.59 in some sort of equation here. Oh boy, it's the 3 people that participate a lot in this class. Let's hear from someone new. Someone I haven't heard from today. I think I've heard from you. Yeah. Two zeta omega n. Okay, that's probably a good starting point. And what's that going to equal to? To what? Yeah, but that's going to give us a fixed value here, right? So that 5 came from choosing very specific parameters for our circuit. So instead of 5, it's 1 over RC here, right? We want to use this equation, right? But right, 2 zeta omega n is 1 over RC. Okay. Right. What's omega n, though? What? So omega n squared was 1 over LC, or omega n is equal to the square root of 1 over LC. Maybe let's combine these equations here together, along with our value for zeta. So 2 times 0.59 times square root of 1 over LC is equal to 1 over RC. Okay. Now what? Remember, I said change one parameter. So we're going to solve for one of them. Which one do you guys want to do? We got 3 choices, L, R, and C. So I heard a lot of C's. I hear 1 R. L. All right. How many people say L? How many people say C? Lunatics. How many people say R? R is probably the easiest one here, right? Because we don't have to deal with the square root thing, right? If we have LC already in that square root, let's just keep that the same. Let's keep omega n the same, right? So this was omega n, right? I say let's just keep this number exactly the same that we had before. What was it? 0.05. C was what? I think I made it 2, right? C was 2. Let's solve this equation for R. What type of resistor do we need in this circuit to make it underdamped, where if we put in a step for our voltage, we would get an overshoot of 10%? You guys want to solve that equation for C. That sounds like a lot of work. You could do it, absolutely. I think replacing the resistor would be the easiest. So what we get? What's R end up being?
8.46.
8.4, I had 7, doesn't matter that much. Ballpark, right? This is the resistor we want to put in that circuit if we were only to replace one of these elements here. Okay? All right. So I am going to upload some additional notes because we didn't get into approximating second order systems or approximating high order systems as second order in this class. I'm going to put those on Blackboard. Please review them because they will be relevant later in the class. So there'll be extra lecture notes up on Blackboard in like the example section or something like that. All right, that's it, folks. Enjoy your weekend. Send me questions that you want to review on Monday for the exam. Exam is up through first order systems. One second. All right, folks online, do you have any questions? Otherwise, I'm going to end the meeting here. All right.